And as I put into that, assume that you're in quadrant number 1. And you're asked to find the other 6 trig ratios, or 5 trig ratios?
Yeah.
All right. So, draw a picture, draw a picture, draw a picture. I'm going to put in quadrant number 1 a triangle with a reference angle, which is my value of theta, which is also my reference angle. I'm going to make the cosine of this angle, which is defined to us as adjacent over hypotenuse. My adjacent side is a value of 1. My hypotenuse is a value of 6. Okay, we have our good old buddy Pythagoras. We have our good old buddy Pythagoras, which will allow us to find the third side here. I'm going to give this a y. So we have 1 squared plus our y squared is equal to 6 squared. Subtracting your 1 over. Y squared is equal to 35. So y is equal to square root of 35. Okay, once we get our triangle set up, then we can use our trigonometric ratios and our trigonometric guardian, sine theta, opposite of our hypotenuse, cosine we were given, tangent, which is square root of 35. Cosecant is a reciprocal to sine, so we have 6 over square root of 35, And then we have to use our algebraic skills, multiplying top and bottom by my radical 35. We have 6 square root of 35 over 35. Secant is reciprocal to this, so we have 6 over 1, which is a value of 6. And then cotangent, 1 over square root of 35, which is square root of 35 over 35. Other questions? Once again, should be a lot of recall from trig class in this. Okay, when we dealt with angular velocity and linear velocity and the circular motion, that was new stuff. That was a little bit more shaky for you. But the other stuff we dealt with the first chapter and first section, and this stuff here, we've done these types of problems. Okay, when we were in trig class, this is what we did. So there should be, one of those things as you go through these problems, it might be a little iffy to start out with, but once you start going through them and start doing the problems, you should hopefully get some recall into what we did in trig class. Hope is you get some recall there. All right, today we're going to start working with our graphs. We'll spend a couple days on graphing. Once again, there should be familiarity to this. The only thing that's different now to what we did in trig class is we're just going a little bit quicker. Okay, in trig class we broke this down a little bit more, so you had a little bit more time to absorb. And this aspect of trig, it's a little bit quicker process. In the college trig, a little bit quicker. But the hope is, once again, second time through, the absorption rate and the understanding will be a little bit quicker in your thought process. They deal with sines and cosines of trigonometric functions in the science and the physics world. This goes into science and physics. We talked about a little bit with respect to earthquakes and logarithms and the idea of logarithms when we were working with them a little bit. You have a trigonometric function because basically your earth is reverberating back and forth. It was reverberating back and forth to the shock of an earthquake. But when you start talking about light waves, you start talking about sound waves. You talk about your heartbeat. Okay, this is all what we call sinusoidal functions or sinusoidal graphs. Okay, your heart rate when you expand and you compress. Hopefully, you have a nice simple harmonic motion with expansion and compression. So your heart and the pump that's in your that your heart is working is working efficiently, and it doesn't expand too much and contract not enough, or vice versa. You have expansion, you have contraction, that should be the same, back and forth. Once again, going into the scientific world, the idea of simple harmonic motion. Pendulums that go back and forth. This is called simple harmonic motion. Springs that expand, contract. That is simple harmonic motion. Okay. Once again, sound waves. When you deal with your sound waves, any types of waves, your light waves, your sound waves, these are all trigonometric functions. So these are all examples of how you use sines and you use your cosines. If you get into the scientific world, you get into engineering, you get into the idea of physics, you'll deal with sine and cosine curves and expanding the sine and cosine curves once you get into the idea of waves. When we are in trig class, we had a base equation for a trigonometric function. We have y equals our vertical face, our BPS, plus or minus a sine or cosine, does not matter if it's sine or cosine, b, and then we have x minus HPS. Okay, this was our fundamental equation that we continue to go back to, and as we expanded what we did in trig class, this typically was written on tops of papers. So it is something that you can refer back to, and I suggest that you continue to do that because it's easier to, get this down and refer to this, and that will allow you to hopefully get all the parts that you need to be able to graph your trigonometric functions of sine and cosines. When we talk about this A value here, this A is your amplitude. It is your magnitude. Once again, it's the idea of a magnitude. It can be proportional to the power of a sound wave. Okay, A is your amplitude. It's a distance from your prime axis to peaks and valleys on your graph. A is called your amplitude. And once again, it's a distance from a prime axis. Now this prime axis is a neutral axis. Well, I'm a math teacher. Neutral axis is your neutral axis. It is what you're oscillating about. It is, once again, the pendulum going back and forth. It is the middle part where your pendulum goes up and it swings the other direction. It is your middle part. Or once again, it's your heart rate. If your heart rate, you compress, you expand. It is that middle part of your expansion and contraction. So this is your amplitude, is distance to your prime axis. And once again, this amplitude a lot of times is going to be proportional to the amount of power that you have in some sort of sound wave or light wave, microwaves, whatever you want to talk about. Second part is the period. The period is the number of degrees from a point on a graph to a point at which the graph starts to repeat the pattern. It's the number of degrees from a point to another point where the graph starts to repeat a pattern. The expansion, the contraction, goes back to expansion, goes back to contraction. You start going back and forth. Okay? What we measure the period in sometimes is our heart rate. Okay? We take our heart rate and we see how many per second. Okay? You can talk about the idea of frequency. The idea of frequency, when you're dealing with a frequency, we won't get into frequency as much, but the period is directly related to the frequency. In the algebraic world, and then also in the Precalc world, when we were in Precalc, we dealt with many types of functions. Talked about quadratic functions, linear functions, exponential functions. We have all these types of functions. Okay, when we talk about trigonometric functions, these are called periodic functions. They repeat patterns over and over and over and over and over again. That is our lives that we go through. We talk about the moon cycles. Okay, we talk about Mickey's big hand and little hand up there. They continue to repeat a cycle. Okay, how long does it take for it to repeat the cycle? How many degrees does it take to repeat the cycle? Okay, how we calculate our period is we take 2 pi and we divide that by b. Okay, this is once again in a radian mode. We will deal mainly in radians in this class. When we were in trig class, we took 360 divided by b. Okay, we took our 360 divided by the b value. Okay, when we're in the college trigonometric idea, we just deal more with radians because a lot of things in your upper level mathematics, they kick straight into radians because degrees fall apart, degrees start falling apart when we get to upper level mathematics. So they deal with everything in terms of radians. We have a vertical phase shift, the VPS that's up here. This is called a vertical phase shift. It's a vertical shift of the horizontal axis. The graph will oscillate about, okay, or that prime axis. It is a vertical shift of the prime axis. And that's once again what you oscillate about. What you go up from, your peaks from it, and your valleys from that prime axis. What we talked about before in the algebraic world, we called this a vertical translation. It's slide vertical up and down of a graph. Then we have a horizontal phase shift, the HPS. The HPS is the value that's being subtracted from our x value variable. What value is being subtracted? This is your horizontal phase shift. And when we talk about the horizontal phase shift, it's the horizontal shift of the graph. It is your degree start value. It is your degree start value. What degree value do we want to start this at? And once again, this is a value that's being subtracted. It's being subtracted from x. So if we have some value x minus 3, your horizontal phase shift is equal to a value of 3. But if you have x plus 3, we are no longer subtracting from our x because it says addition there. But how do we convert this into a subtraction? We can write this as x minus a negative 3. If we have x minus a negative 3 minus a negative, we'll turn it back into a positive. Our horizontal phase shift is a value of negative 3. And once again, going back to what we talked about with respect to sine and cosine curves. Okay, when you have a sine curve, your graph will start on this prime axis. The graph will start on the prime axis. For a cosine curve, the graph will start at either a peak or it will start at a valley. And once again, the hope is, as we go through this, there's things that are kicking back in your brain that is somewhat of a recall. Do you remember how to fully graph sine and cosine curves? Probably not. Maybe you might. But as we start to go through these things and the keys that we go through, hopefully you'll start to remember the things that you have to do and the process you have to do to get your graphs down. Find all pertinent information in graph. Y equals 2 plus 3 sine pi over 3 x minus 2. First thing we want to do is find all the pertinent information. We want to find the amplitude, the period, the vertical, horizontal phase shift. Well, the amplitude is our A value. So if we look back at our equation, we have y is equal to vertical phase shift plus or minus A sine or cosine. It does not matter because the graphs of the sine and cosine are just shifted 90 degrees one direction or another. We have this B value and then x minus the horizontal phase shift. So if we look at this equation, the first thing we want to find is the amplitude. Okay, Malt, what's our amplitude? 3. Yeah, here's our A value right here. That's the value 3. Vertical phase shift. Colin, what do you have for the vertical phase shift? 2. Here's our vertical phase shift here. We have a value of 2. Horizontal phase shift. What's our horizontal phase shift, Ava? 2. Our value that's being subtracted from x, we have a value of 2 there also. Let the period for the last one because this one's a little bit more mathematically, or you have to deal with this a little bit mathematically. How we calculate the period is we take our 2 pi and we divide it by our b value. Well, our b value is pi over 3. So we have 2 pi divided by pi over 3. Well, we're dividing by a fraction. Well, when we're dividing by a fraction, what do we have to do mathematically to divide by a fraction? Takes it back to early math.
Change it to multiplication and flip the other fraction.
Okay, we got to 2 pi times 3 over pi. We flip the second fraction, and we turn it into multiplication. Which now allows us is we have a pi on top, we have a pi on bottom. The 2 pi's go bye-bye. They cancel out. So we're left with 2 times 3, which is a value of 6. Okay, if you remember back, dealing with the graphs, you look at the amplitude and the vertical phase shift to try to shift your graph a little bit. Vertical phase shift of 2, we have an amplitude of 3. So we have to be a little bit more top heavy here with respect to our graph. We have our X and we have our Y. The nice thing about dealing with radians, if you remember back to dealing with radians, is we don't have to worry about big numbers, degree measures. So we can count out by ones. The vertical phase shift and the amplitude will tell us what we have to count upwards. Once again, we can count by ones. Now we have to start dealing with some recall. Do you remember what the first thing we put in our graph? Now you just had this. Let's see if anybody else remembers. What's the first thing we put on our graph?
Is it the prime axis?
Prime axis. What do we look at for the prime axis? Vertical phase shift. So the first thing we take a look at is the vertical phase shift. Tells us where we're going to draw in our prime axis. Once again, this is the axis that we will oscillate about. We will go up from this, and we will move down from this. We will move up and we will move down. Second thing, do we remember? There's 2 things we take a look at. Where do we start our graph? What x value we start? And we also look at the trig function. The horizontal phase shift tells us where do we start our x value. We started at 2. The trig function sine tells us we start on the prime axis. So we have to start at 2, and when we deal with a sine curve, we start on the prime axis. So at the value of 2, we are on the prime axis. Third thing we take a look at is at the period. Okay, by definition, a period is defined to us as the portion of the graph from where it starts to or a point where it starts to repeat itself. So every 6 units, we will be at the exact same spot. Well, if I start at the ordered pair 2 and 2, and I go 6 units to my right, what y value will we be at, Noah?
You'd be at a y value of 2 again.
2 again. So if I move 6 units to my right, I will be at 8. I will still be at 2. If I would go another 6 units to the right, to 14, I would be at 2. If I would go back 6 units to -4, I would be at a value of 2. Every 6 units, I will be at a value of 2. Okay, next thing we worried about and we worked with was the gains of halves. The gains of halves. Halfway between 2 and 8 is a value of what? Remember? 5. Okay, do you remember where we're at with at the value of 5? We're at 5. That's our halfway point. Okay, let's go back up, and I guess I should have put this up here. We deal with a sine curve. If you remember a sine curve, what we do with a sine curve, we start on the prime axis. And the roller coaster ride, we start click, 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 climbing the hill. And then we go into scream mode. We go underneath. And then we come back up again. Cosine curve, we start at our peaks. So we climb the steps of the roller coaster to the very top. Cosine curve, we start at a peak, and we're automatically in scream mode. And then back up again. Your prime axis, once again, you have to go above it and you have to be below it. So going back to our question now, our gains of halves, because we have to be symmetrical. Hopefully we're symmetrical. Hopefully your heartbeat is a symmetrical heartbeat. Hopefully it is. If it's not, you're going to have trouble. At the gain value of 5, where are we at then? Evelyn? At 2 again. Then we do our gains of halves between 2 and 5, halfway between 2 and 5. So that's what's our halfway point.
3.5.
3.5. At 3.5, where would we be at 3.5?
On the top.
At the top. How far do we go up? Well, we can take a look at our amplitude to tell you how far we go up.
To 5.
Up to 5. So if we're at 2, we have to go this amplitude of 3 up to a value of 5. Second, last game it has between 5 and 8. The halfway point between 5 and 8 would be where it going?
So, oh wait, 6.5.
6.5. And what would be our y value? This one took us up.
-1.
-1. We have to go our amplitude downward. So we have our amplitude up and then our amplitude down. So we have to be 3 down from 2, so we go down to -1. And now we can construct our sine curve. Once again, the hope is you start to recall some of that stuff that we did in trig class. Okay, reciprocal functions. Reciprocal functions for secant, we use cosine. And for cosecant, we use sine. Okay, the reciprocal function, secant, we go with cosine. And when we deal with cosine, we deal with the sine there. Or cosecant, we use the sine. Okay, we use these as our guide functions. Okay, these are our guide functions. Okay, and the other thing to remember with respect to our guide functions, where the graph of the sine and cosine curve hit the prime axis, what we got there was asymptotes, vertical asymptotes. Where we hit the prime axis, our vertical asymptotes were formed. So if we take a look at y equals 2 plus 3, secant pi over 3, x plus 1. We have a secant, so we're going to use cosine as our graph, as our guide. Write down your pertinent information. What's the amplitude, period, vertical, horizontal phase shift? Check your answers with somebody around you. Alex Cross, amplitude, period.
3 and 6.
3 here and 6 here. Taking 2 pi divided by pi over 3. You get a value of 6 again. Vertical, horizontal phase shift. Courtney? Vertical is what? Horizontal? -1. Once again, this is x minus the -1. So what we want to get down here is we want to get our cosine curve down. Let's see here. Amplitude of 3, vertical phase shift of 2. So we want to be a little bit more top heavy again. First thing we draw in, a vertical phase shift. Draw on your prime axis. Second thing, our trig function cosine and our horizontal phase shift. Okay, we start at -1, but we have to start at a peak. So our peak is at an amplitude of 3 up, so we're going to start at what, Brady?
5.
At 5. Look at the period. If we go 6 away, we have to be at the exact same spot. So if we're at -1, it goes 6 away. We should be at the exact same spot. So that should be at 5. Gains of halves, halfway between -1 and 5. We should be at our valley. So you take them, add together, it gives me 4. Divide by 2 should be at a value of 2. Halfway between 2 and -1, we got a 0.5. We will pick up there tomorrow, and we'll finish our notes tomorrow. We have no homework tonight. Sorry to disappoint. We'll pick up there tomorrow. Finish graphing your cosine curve on this last one here. We'll pick up from there. Have a good day, everybody.